Good afternoon, audience who have come from your different walks of life, leaving your work to hear from the legend. I welcome Mr. Jose Korean on behalf of QCrete India Private Limited for delivering this lecture. I will just have few words about Mr. Jose Korean. Really, if we want to tell, Mr. Jose Korean doesn't need an introduction. He is a walking legend and I can say walking encyclopedia in civil engineering. But as a formality, I'm trying to introduce Mr. Jose Korean sir. Mr. Jose Korean sir is graduated in civil engineering from NIT Calicut in 1986. And he got MTech in structures from IIT Delhi. He also holds PGD in earthquake engineering from International Institute of Seismology and Earthquake Engineering, Japan. He was involved in some very important structures like Jawaharlal Nehru Stadium, ISBT flyovers, renovation of fire damaged Vigyan Bhavan, Parliamentary Library building, Madhuban underpass, 1.2 kilometer long Lajpat Rao Nagar flyover, two underpasses at Peramburial and Moolchand intersections on Ring Road, Delhi. List is very big. I'm just able to read some points actually and some works only. He was the chief engineer for conceiving, planning, designing, and construction management of the signature bridge across River Yamuna at Wazirabad in Delhi. He was also chairman of many BIS committees on cement and concrete. The list is exhaustive and we cannot list at this point of time. He is a former president of the ICI. He has received the prestigious Lifetime Achievement Award in 2016 from ICI. He has also received, I can say, one of the most prestigious awards for civil engineers, the CITC Vishwakarma Public Officer Award in 2011. He has authored a lot of books, over 50 technical papers, presented in conferences and published in journals in India and abroad. And with this introduction, I would say the webinar is open today and the floor is yours, sir. Mr. Jose Korean, sir.
Thank you, Coach. Good afternoon to everybody. This is in fact a continuation of what we have done in the last session on Signature Bridge. So quite a few of you would have been listening to me at the last time. So in the last discussion with the organizers, we thought that we'll divide the entire the bridge history into two parts. The first part we have already done last month on the planning and design of the bridge, and today we are going to present the part of this Signature Bridge saga, the construction and innovations that has been done to create this iconic structure in Delhi. So as you know, it is a very important structure, a unique structure, a signature structure created in the capital of this country. And as we have discussed last time, we have gone through a whole lot of difficulties and a whole lot of innovative and creative work has gone into creating this particular structure for this country. And I will just thumb through that a few seconds, few minutes, so that the people who were not there last time will get an introduction to that one. And then I get into the second part of construction and innovations that has been implemented in this particular project. The lecture is supposed to be for about an hour plus. I hope that the time available, we should be able to cover what we are planning to do today. And at the end, there are question answer session. I think the organizations will take care of that one. So if we had last time, one moment. This is not working. Okay. The agenda for the day would be a brief introduction on the project, on the bridge, and the concept on the structural system, execution and innovations, and the people who have contributed for this project in a very brief way. So that is the idea. And the project is so huge and so innovative and so complex that it will take quite a few lectures to cover the whole thing. So my idea would be to just go through what are the major points, major highlights of this project. And many of those issues that we are going to discuss today will require a lecture of its own. Maybe some other time when we have more time, we should be able to think of doing that in detail. So quite a bit of innovations, but I will not be able to go very deep into those innovations and how it has been done, carried out. I will just briefly mention what the issue is and how the issues were solved and what are the new things which were brought into this particular project. And so it will be quite brief, and I must excuse us because of the time limit and the vastness of the complex project. So the Yamuna, as we have discussed, is a part of the Delhi, and this river is part of the culture and the history of Delhi. And we at the Delhi Tourism and Transportation Corporation, DTDC, were assigned to do this particular bridge quite some time back, and we have started working on it. And after the discussions and the preliminary discussions and investigations, we have taken a call to provide a bridge somewhere below the Wazirabad bridge, which is the northernmost part of Delhi, and where the Wazirabad barrage is there, from where the Delhi used to get the complete drinking water. So about 600 meters below, we thought that we can site this bridge. And this being an important link between the eastern part of the country with the north, attracts so much of traffic, especially goods traffic. And today the Delhi eastern side is also very heavily populated, and they also come to Delhi, to the Delhi side, the western side, to work. So we have done the traffic study and decided, after the geometrics, everything has been done, a decision was taken to provide this bridge 600 meters downstream of the Wazirabad barrage, and connect it with the ring road on the west side, and the eastern ring road, and the ring road on the east at the Khajuri Khas junction. So that is the geometry, that is the alignment which was decided and approved. And based on this one, yeah, the project as such, right in the beginning, was a complete tourism destination for that part. And after the project, the entire the concept was prepared and presented to the Delhi government. It was decided to divide the project into two. The one is the tourism destination, which has got a number of very, very unique tourism elements, and another is the bridge, a bridge to be done. So a decision was taken that for the first part, do the bridge first, and then we can take up the tourism destination part later. So decision was taken. Then we started working on detailed design of the bridge. So this is what has been done. So, and right in the beginning, we have divided the entire project, the bridge project, into three. The western approach, eastern approach, and the bridge, the bridge there. So these were the three things, and we know that the bridge became a signature bridge. We have discussed in detail what has happened and how it became a signature bridge. It is because of the background of the Commonwealth Games, and the Chief Minister of Delhi was very keen, Mrs. Sheila Dikshit was very keen that we should create a structure which has not been done elsewhere, anywhere in the world. So that challenge was taken by the consultants and the Delhi Tourism, and it was decided to have a signature bridge which should become a signature structure for the entire for the capital of this country. So that is how a signature bridge was, the idea of signature bridge was born, and it was decided that we will have the signature bridge sited here with two other projects of western approach and eastern approach. So the whole of the bridge project itself is in three parts: western approach, eastern approach, and the signature bridge. So on the western approach, it is a set of flyovers so that you get a completely signal-free approach to the bridge from anywhere. Similarly, from the bridge also, you can reach any part of the ring road without any signal, in addition to cycle traffic. So the whole component has almost tilted portion itself is about 13 lane kilometers, and the RE wall embankment is about 1.8 lane kilometers. Road at grade is about 12 lane kilometers, and there's a cycle track of 3.5 kilometers. And on the eastern approach side, we have a roundabout, a huge roundabout of almost 100-meter plus, and the components are: there's a tilted portion of about 5 kilometer lane length, and embankment of about 12 lane kilometers, and RE wall of 1.8 lane kilometers, and grade roads of about 20 lane kilometers. So this is that part. And we come to the structure that we are going to discuss today, the signature bridge. So after a lot of discussions, which you have discussed in detail last time, it was decided that by a high-powered committee, including the cabinet of Delhi, that a structure of this particular shape will be adequate, which will be good, and probably that kind of structure is not existing anywhere. So this is a slightly backward slanting unsymmetrical pylon, unlike the normal cable-stayed bridge. It is a cable-stayed bridge, but it is unsymmetrical, totally slanting backwards, and with a set of cables in the front, supporting a free span of 251 meters, and 4 pairs of backstays to take care of the variations in the loads. So ultimately, structurally, visually, it is a very, very striking and beautiful, dynamic looking bridge. And in the structural view also, it is highly, it can be said that is a very, very ingenious and dynamic concept, because what is happening here is the weight of the pylon is carrying the weight of the deck. The pylon is trying to fall back, which is kept in place by the deck, and vice versa. This is any change in the load due to live load or any other thing will be taken care by the set of 4 sets of backstays. So this is the concept. So it is a structurally dynamic structure. So, and very, very striking and very challenging, and both in its design as well as in its execution. So this is what has happened. So this is some of the views which were developed. Whole idea was that it is the shape is in the form of a namaste, a folded hands, welcoming all the people to Delhi. So this was the idea behind one of the idea behind the signature bridge, that it will be a welcome bridge for all the people of Delhi. So this is the way it should look like. This is what has happened. And we also created some night view to study how it look like. It will have a viewing platform on the top, totally glass, almost 25 meters high. So this is the concept, and people can go to the top through the lifts within the structure, reach the top, and have a nice view of the city of Delhi. This will be almost 165 meters above the river level or deck level, so almost twice the height of Qutub Minar. Qutub Minar is about 75 meters, and this comes more than that, about 165 meters. So this is the basic concept which is approved. So this is the way it should look. This was the idea, and basically look at it. The designers have been very, very ingenious, that they were able to such a complex thing. They have simplified in creating the structural elements to decide the load path. So essentially, it is like an open book on the top, 2 sheets trying to open or close, and which is supported by two legs which are splayed in either direction and held in position, pulled from other direction by one cable set of 16 sets of cable, held back by its own weight of the structure, and variations taken by the set of backstays. So this is the concept that has been decided. Apparently very simple, but at the same time only I mean that hats off to the designers who have done such a simple concept to get a complex design done. So this is the way to look like a very, very, very welcoming namaste to all the people. So this is the idea. And the architectural things were finalized like last time we have discussed. And the same thing was converted into a structural system, a line system in which it will have a 251, I mean, the structural system will be a line sketch which is produced from the architectural concept. And this is the way it will look like. You have a pylon. I will have a better picture. Yeah, we have a pylon which is have two legs, which is splayed in both directions, going up all the way and joins somewhere in the middle. And from there, the steel pylon rises, and the set of stay cables, 16 set of stay cables in the front, 4 sets of backstay cables, and the top glass fascia. And on this side, on the left, you will see that the bridge ends there. There is a 1 meter wide expansion joint because of this 251 meter span. The 251 meter span, it has to take care of the expansion and contraction due to temperature. So the expansion joint on this side is almost 1 meter wide, and a very special expansion joint has been put there. And the entire foundations are partly in wells. Most of the foundations are on well foundations, but at the two or couple of them will be, 3 of them will be. This is the main pylon foundation, and the next one as well as one on this side, P3, will be on open foundations. So that is the way the whole concept is there in very, very simple terms. These are the basic elements. So in terms of the dimensions, this is the way it will look like. You can see the cables and the pylon head, the cables and the foundations which is there. So one of the issues which has confronted the construction was pylon. I mean the backstay ends here, and backstay will be in tension, and the entire tensile force will have to be held down by a huge deadman here. So creating this one has created a major design challenge and construction challenge. We will have a look at it later as we go along. So the deck itself is a marvelous structure. It is 36.2 meter in width. That is normally a longitudinal span of a normal bridge, the width itself. So it creates 8 lanes traffic plus 2 service lane. So that is the way it has been created. So the concept is to have a single deck. Normally, a bridge of this type will have 2 decks and 2 sets of cables. I mean, 2 sets of bridges will independent bridges will be there, like in Bombay or anywhere else. But the problem is, while traveling through such bridges, one get a very, very complex view of the entangled nets, which is cable nets, which are coming while you drive along. So the architects and the designers decided that let us have a clean image while traveling through the cables. So it was decided to have only 2 cables on either side, 2 cables on either side only. So that is why it was decided to have a wider deck of 36.2 meters, and the entire deck structure is created in steel. We have the main beam coming along. This is the main beam. This is another main beam, which is being pulled up by the set of cables. 16, I told you, the 16 sets of cable pulls up this beam, and this is quite a big beam. And then there are cross beams, and then there are diaphragms beams are there, which goes and connects a set of a steel deck is created. Over that, a concrete layer is there, concrete pavement is there, concrete deck and pavement is there. So the another concept which has been created for the first time is that this is a composite steel concrete composite structure, but at the same time the concrete is precast. So maybe such a large scale first time it has been done in this India, even though it has been done elsewhere in the world. We have in India for the first time we have tried to do a steel concrete composite deck using precast decking. So this is what has been done for the decking. And then the structure was divided. Detail. We went into detailed design, and various sections were evolved and used for those sections analysis, simple analytic analysis, and other issues where we have discussed last time. We have done the design, and then it is verified by a very detailed 3D finite element analysis. For reaching the calculating the forces, we also done detailed earthquake analysis. Response analysis was done. Even a site-specific seismic study was done by the University of Roorkee. And for the wind, detailed analysis, a wind tunnel test was done in Germany. We will last time we have discussed the implications of those studies which has been done, and using all of them the forces were calculated, and simple studies we finalize the sections. The designers have finalized the sections and the thicknesses of the plates and everything, which was again verified by several times by iterations and finally validated through a three-dimensional finite element analysis. So this is what has happened. So these sections were done already. Detailed drawings were prepared. About more than 1,000 sheets were prepared, and this had to take into account while designing the construction methodology. So while designing and detailing, the detailing was done with completely the construction methodology, the erection methodology, the fabrication technology, all those were in consideration. With all those things in place, only the actual structural drawings were issued, so that the design that we create, we should be able to implement in the construction when the construction is carried out. So that was the basic concept, and a whole lot of detailed engineering had to be done. And much more than one of the most important thing is the importance of enabling structures. As much probably practically substantial amount of steel structures were to be created as enabled structures to erect the structure. So that also had to be kept in mind to simplify their systems and economize the systems. So the structural design was carried out with all these things in place that minimize the enabling structures and take into consideration an easy and straightforward erection system. And from there, for when creating those pieces to erect, look into how to fabricate the same, and so look at the materials and how to fabricate the same. So a designer had to look into all these aspects, the constructability of the project, while doing the detailed design. For this, we had a very great help from the Professor Miranda of Italy. He has done a fantastic work in creating the entire enabling structures were designed by him, and the complete detailed engineering was done by his office from Italy. And the bridge is one of the major innovations that has been done. We have tried to discuss last time. This time it's important. So what we have done is we have, for erection purposes, the entire pylon was divided into segments, 1, 2, 3, 4, like that, from bottom to top. So, and we have a junction here where the two pylons meet here, and then the Namaste begins. So that was the longest joint here. And then there were pieces which were created, which were to be fabricated, checked, and brought here and assembled here. So this is the way it has been done. And the detail, if we had done the normal way of putting these pieces together, we would have required a whole lot of plates and a whole lot of bolts. So with the result, with the kind of size of the segments, practically the entire surface of the bridge would have been covered with only bolts. So this was an issue which was discussed, and the architects were not ready to have it. So thereby, idea was brought in to directly transfer much of the dead load from one segment to another by providing a mating surface. The top and the bottom should mate so that the entire vertical load is directly transferred into the bottom, and very little of bolting that can be seen outside. So this is one of the major innovations which has been done. Unlike in many places where the segments are connected through bolts, here it is directly transferred. But a price has to be paid for this one because of the surface which we are going to create. For mating surface has to be absolutely plain, and for which we will require extremely heavy control, geometry control, and very heavy, very sophisticated equipments for this one. We'll see that later because of the size of the joints. Some of them are over 20 meters, and the entire 20 meters have to be planed to get almost a millimeter per meter accuracy. Some places even tougher than that one. So that was possible only through geometry control. We'll come to that one, and using machines. So we'll come to that later. So these are some of the major innovations that have been done in this project. So this is the way it is there. You have the plates, and the plates are bolted inside, so you don't see much of the bolts outside. So it speeded up the erection because the less number of bolts, it takes less time to connect the segments and go up. So this is the idea. And we also save the material because of the plates. The cover plates have been reduced to the minimum, so a whole lot of steel has also been saved. But it may not have saved much cost because of the finishing, the tough tolerance that are required there, which require very high level of machining and time required for the same thing. Another very interesting thing that has been done here is the pendulum bearing here. So this is where the stay cables at the back comes and joins the deck here. Now the problem is these stay cables pull. There's a tension in the stay cables. Will try to take the bridge up, the deck up. So it has to be held down, and to hold it down, you require a dead anchor, which is a very heavy weight. That entire load has to be resisted by a dead anchor with so much of factor of safety. The added difficulty is that the bridge is a moving bridge. Because of the temperature, the bridge deck will be moving along the longitudinal direction. So it had to take two actions. One is it should take the entire tensile load which is coming here, it should be pulled, and that pulling load should be transferred to the dead anchor. At the same time, the bridge should move as the temperature rises. So that is why this pendulum hinges, pendulum bearing has been created. It's a huge structure, but it has been executed successfully here. There are two pairs of this one here on either side, and these things here, base can move. So even if it moves here, it can move in both directions without any difficulty. So but the entire bearing is in tension, and the entire bearing is in tension, and through this pendulum it has been transferred back into the dead anchor below. So this is very interesting work here. And the another one which you have discussed already is the decking for the steel concrete composite structure. Here what has been done is that the entire decking is precast, the whole lot of, except when a very small places in situ concrete has been used, but otherwise the entire decking concrete is precast. So what has been done is these beams are going, longitudinal beams and cross beams are there. You create rectangles here, and in these rectangles you provide the precast slabs, and then it is connected to the deck through shears. Shear bolts are there, and then in situ concrete is done between the two elements there. And there's no shuttering is required because the top flange of the beams will act as shuttering. So all you have to place the elements there, see that they are enmeshed between the two, and the bolts are available, shear connectors are available, concrete it. So that gives a very faster and very quality structure. So that was another major innovation that has been done in this project. You can see the number of elements there. The dimensions vary in some places, so that had to be numbered and taken care and cast in the precasting yard. So that was a huge effort, but it has been done very successfully. And we also done on the painting work has been done on this bridge, because it is a iconic structure. Yamuna's motif of the peacock feathers were painted onto the structure, so it has to be done along with the painting, which is a durability factor. So this action was also done, very interesting. You will be able to see that later as we go along. So the total reinforced concrete was about 45,000 meter cube, reinforcement of about almost 5,000 tons, and structural steel of almost 14,000 tons were used. In addition, thousands of tons of enabling steel was used in this one, and various grades of steel. Some of them are very, at the time, were not available in this country, or even in China it was difficult. It has to be specially ordered. Very special, high quality steel were used for this one. And the expansion joint between the main and the approach, also western approach, is also very complex, because from there it goes into a sharp curve. At the same time, it's also split into 3 different bridges right after the expansion joint. Creating that and adjusting the whole thing in the expansion joint was very interesting work, which has also been done successfully. So it is a very innovatively designed. Lighting is provided for normal, weekend and festive ambience levels have been provided. So that is already available here. One of the most unique thing is the bridge health monitoring system, which will take care of all that is necessary, and which will also validate the whole design that has been done so far. This itself is a huge topic for discussion, and as the data is flowing in, we should be able to present the bridge health monitoring system live later some other time. So there are a lot of things are measured here. The wind, temperature, and the rain, precipitation, and the cable force are measured. Vibration and the temperature and the traffic are also measured here. Displacements, extensions, and the movements, corrosion, seismic measurements, relative humidity, all those things can be measured by sensors, and the whole thing, the data is being transmitted alive at every time, and it goes into a computer. Right now it is not in India, but from there the data flows back into the bridge maintenance unit, and it will give you a dashboard on which these factors are available. And whenever there is an issue which requires attention, a trigger will come and you can take action based on that one. It's a very detailed system. So it measures the environmental conditions, displacement, distortion in geometry, the accelerations, the loads, corrosion, and fatigue, as we discussed here. And there are other issues are there. The lifts were to be put capable of incline travel, a detailed cleaning system, stay cable cleaning system, and arrangement to lift the weights, and robotic cleaning units. These are all for inaccessible units to be done. These are all being done. Now let us get into the construction mode. That is the part 2 part of it. And if you look at it, the bridge looks like this when it is to be done. Construction is to be done. This is the pylon, the main pylon, inclined pylon and symmetrical pylon, which is supported on an open foundation, which is a very interesting work that has been done. It is almost 16 meters below the level, the bed level, and the 16 meter and the water level is at the ground level. So going down all the way to 16 meter down and constructing a huge foundation for the pylon was a challenging job. It's a very interesting thing. We'll do that. And then we already discussed about this P23, we usually call it, this creating this one because of certain specific problem which encountered when we went for construction. So that is also very interesting design. And then there are a number of well foundations which is normal, but they are all very big wells, not the normal wells. And many times we had to do many innovations to get this project done. So we'll have a brief look at how these things were done. So the well foundations, you can see, because of the time constraint, because of the you get time only in between the flood time. So most of the well foundations were to be taken up simultaneously. So you can see the activity which is going on bustling activity in which most of the wells were started simultaneously and work is going on simultaneously in each one of them. They are all in different completion. So the different wells are in progress, and normally the sinking with Kenlet, of course, reinforcement, and then concreting. This is the activity going on round the clock and balanced among various things so that this activity is one after another. It's a very, very complex project management system in which you see that everything, right from the concrete production, steel bending, and the Ken ledges, everything had to be aligned so that the work goes fast. And the concreting is being done in one, another place the reinforcement is being done. So this is the typical well sinking process by Ken ledges, and it has been done successfully. There were no problems. These are various scenes, and then the concrete had to be cured, and the work is going on. They are all unusually high diameter. Most of them, the biggest one, P23, is almost 23 meter in diameter. Rest are almost 16 meter and 12 meter. So these are all unusually large foundations, large wells were to be completed, constructed. The most so this is typical well curve only. Normal curve we will have about a meter or 1.2 meters, but you can see the size of the well curve itself. It's a normal, I mean, one of the wells which have been done here, the curve height itself is so high. You can see from the size of the people and the work that is involved, enormous amount of work involved in creating the formwork and other things for this well is very, very ingenious. And then the work goes on both in the daytime and in the night, and with a completely project management mode. And this is the typical shuttering for the height, one typical pour, and the shuttering is to be prepared for this one. The staging is to be done for this one, concreting, and then pushing it down through Ken ledges. So this has been done. This is the typical steel. You can see the amount of work involved, so much of labor involved in creating the reinforcement for a large well like this one. You can see the size of the people versus the size of the well. It's a huge effort which has been done here. And when we come to the open foundation, which is very interesting, we had to go down 16 meter right in the middle of the river and underwater. The water is standing there. So the only way has to create a barrier against this water around this particular pit. First, that has to be done. So this is an effort to using the vibro hammer to drive down the sheet piles. So with the sheet piles, you created an enclosure and then dig from top to bottom. So this is the typical top to bottom construction methodology was employed here. And you can see the work has just started. The first vibro pile, I mean sheet pile, first of the few sheet piles are being driven into the ground. And this is the way that the piling is done. Sheet piling is done using a vibro hammer, and things are going down one by one, which are linked together. And first, this is the thing, and then once the complete, all the four sides are completed, like this, a barrier is created. We can start digging, and veiler beams are done so that as you go down from top to bottom, you do the excavation. You keep your sheet piles in place by veiler beam and a very, very, very sturdy veiling and other steel structure, so that the enclosure remains in space and the excavation is going on. At the same time, you should not forget that the whole thing is underwater. Water is there at the ground level itself. So the water which is coming and seeping through the sheet piles had to be continually removed, and the excavation is also to be done. A very, very challenging work, continuous work, and the whole thing has to be completed underwater. So this is what has been being done. And then it's a typical thing. It's goes down to the machine where water comes. It has to be pumped out and excavated, and continually you do it. You inch by inch you go down and go to the different level, and then you start your pier. This is a smaller pier. Actually, for the pylon pier, the main pylon pier, this is the size. You can see the footing that has been done there, and the kind of size that is involved. This is the footing for the one of the footing. There are two footings. One of the footing for the pylon. So the amount of concrete, amount of steel, and the amount of human effort that is required in creating a structure 16 meter underwater and then come up has been a huge challenge for the whole project. And you can see the reinforcement is being done. You can look at the size of the people versus the size of the structure. And then one by one, it's a hollow pier, and it has come up inch by inch. So this is the P2. Now we come to the pylon has been completed. Now we come to the P23, which is a very challenge, an unexpected challenge, which has come in the way, which has shook the project like anything. The problem was geotechnical investigations initially could not be done because the forest was there. We were allowed to do only single bore at each place. But while doing this work, detailed work here, when we have afterwards, the permission from the forest department came much later. When we done the detailed analysis, detailed investigation, we found a major surprise that the rock is slanting. We had to provide a well because that is the only way to handle the dead weight. So the well, when we do it, will not be able to get a horizontal surface onto which you can put the well. Only two solutions are available. Either you dig into the rock till we get the horizontal surface, which is impossible because the rock is inclined almost like 45 degrees, and it is impossible. And with 23-meter diameter, rock can be cut underwater to seed the well in place. So it was not possible at all. So that is why a very innovative solution was worked out, which has been tried once in the Jogipopa by the governments themselves. It was a very challenging, detailed engineering work. It was decided that we will have a combination of well and pile. So what has been done here is, so this is the way, this is the way the rock would be there, rock profile. After investigation, it was found that the rock profile will be something like that one. So one end, when it touches here, the other end will be hanging in the air. So it was decided that we will have 16 piles in each of the wells, and these piles can be driven after the well reaches here. The piles can be driven into the rock to create a pile system onto which the well can be supported, and it can be cast from the top. So this was the solution, which came out after the huge variations that's been confirmed from the geotechnical investigation. So after this, so one thought was to break the rock, which is, we found it's humanly not possible, but only way was to create this well pile system, which was found feasible, but with enormous amount of inputs that are required there, because each of these piles will be very big. 1.2 meter diameter pile had to be cut into the rock substantially, because this has to take into account the load as well as the shear. So that was the issue. So the 16 piles in one well and 16 piles on the other to cut 1.2 meter diameter substantially deep into the rock to get a grip was a problem. And at that time in India, we did not have any kind of equipments to do that. So we had to create to bring in equipments from abroad. I mean, while the work was, I mean, we had to literally, we found the work stalled there because of the P23, and we had to import two machines which can cut the rock and create this well pile system, and we had to wait for that one. And when the machines came, the project was complete. Project could be completed. The well P23 well could be completed. So the idea is to have a well which will be standing on the top, and from there the piles are driven down into the rock with the full grip length, and the well will be supported on pile system. So this is the thing. And then concrete have the usual plug here and complete the project. Apparently looks simple, but extremely difficult to execute because it requires heavy machinery. So we brought two machines from abroad, and Boma 2 rigs from abroad. And only after these machines arrive, we could drill through the pipes which is kept there. We'll have a look at it with this the tubes were kept there right while casting the well, right at the curb from onwards. These tubes were there, and through the tubes, after the well has reached the rock level, the piles were driven into the rock using these Boma 2 machines. So this has been a very challenging and very heavy engineering work that has been done there. And to take care of the shear in the pile, we had to use a cruciform, a typical X-shaped, cross-shaped steel structure inside that, plus steel, and the whole thing has been fabricated. You can see on this side, it is lying here. Lying here, and taken it up and send it down through the pipes. So while creating the well curb itself, all these 16 pipes were to be incorporated in the well curb. So you can see them, the amount of fabrication work required on this for this well curb itself. It's a very complex fabrication of steel which has been done, and then this was sent down to the rock level. You can see the structure with all the people working there. As comparative size is available between the man and the tube sizes, and this is the way it looked just before sending it sinking starts. And slowly the sinking started with heavy measurements and balancing work every day. Slowly it goes down, and then it comes up. It goes down and the concreting is done, the well is being cast, and one by one the whole thing comes up, and the work has been completed. On the top of that, we had to provide, the two wells were connected by a very heavy concrete well cap, and on the well cap at the center we have a column, short column, that is under tension, and on the top of that is the pendulum foundation. Pendulum bearing will come, which will connect the deck and this well foundation. Very challenging work, very interesting work, but it took so much of creativity and pain and effort, both in terms of engineering and administrative skill, to come out of this dilemma. But finally, successfully, this has been completed, and this is the way the place looked at that time. And when it comes to fabrication, we have tried to get the bridge fabricated in India. But when we looked at the enormous effort required in getting a very accurate and quality staff here, even though visited most of the major fabrication yards in this country, we could not get the proper place here. We visited also several other countries, nearby countries, in the Gulf countries, Italy, many places. Ultimately, we found that the kind of size, the kind of output, the kind of mechanical arrangement equipments were available at that time only in Shanghai, only in China. And finally, an arrangement was made with ZTSS workshop in China, a huge facility, and very willing to undertake work because they wanted to learn of all the things. Even for them, it was a novelty, but they also wanted to learn it, so they took up the challenge and done an excellent job. So that is what I must say. A lot of effort, but of course, a lot of effort is required from the Indian side. A lot of quality assurance had to be done by the company, and a lot of effort were to be taken by the Chinese. They had to invest a whole lot of money in many of the new machines they had to bring from abroad to get the quality work done. It's a huge effort from their side. So look at the size of the structure. This is the first block which has been kept on under the pylon, one side of the pylon. The weight is 450 tons, one piece. So the whole thing had to be fabricated. And here the issue is fabrication, so that when the entire thing is fabricated, what we want is available here. That means the whole thing had to be converted into drawings, detailed shop drawings. A huge effort, and only with major software like TIPLA and other things they could do it. And the whole thing has been done. Publication drawings were created, and cutting plan was made, and very detailed geometry control had to be put in place. The regime was very tight. Many times arguments and problems were there between the two parties, but ultimately the whole thing came out. You will see that it fitted like anything. But the pain that had to be taken was huge. So this is a simple, I mean, this is a single piece, 40 tons. And this is the kind of complexity in this one. This is the bottommost piece of the structure on which will be supported on the bearing, and the pylon, one leg of the pylon will come on this one. So the plates were to be done, and the quality started right at the factory where the steel plate is prepared. Our quality assurance team went there, took the samples right at the ladles and tested it, and then only the plates were allowed to be moved from there. And here it came, and they were doing. We had engaged one of the best teams in the world. You can say the Lloyd Register, who has done the complete quality assurance of the entire welding and painting. And hats off to them; they've done a wonderful job. And the geometry control was with an expert from Canada, and he too has done a wonderful job. And the whole team learned a whole lot of things from these two vendors. And this is the kind of steel plates had to be used. This is one of the plates which comes at the bottom, and you can see the thickness is 25, that is 10 inches. One single plate of 10 inches thick. So this is the kind of plates were to be created, and then this kind of things had to be welded to create the structures that we wanted. And this kind of facility was not available at that time in India, and even the plates of this thickness are still not available, because creating that itself is a challenge. And then to get the quality done, the sufficient quality metallurgically, is another job. But anyway, the company could produce both the steel as well as the fabrication. So this is the way it is done. You can see the bottommost piece, the kind of spaces in which people are to sit down and do the welding. Hardly a space to sit there, and you have to do the welding sitting there, and several runs have to be done. It's not just one run, two run. It's such a hot environment. You have to sit many times, and then the quality assurance team will have to go and check each place that the welding is correct and record it and pass it, and then another auditor will come. So this is the kind of work, very involved work that has been done there. You can see the bolting, and you have to see that these bolting will have to mate with another thing. So that is the kind of geometry control, complex thing, because it also involves temperature, because temperature will distort the whole thing. So the geometry control guy has to take into account the possible temperatures, anticipate them, and create this geometry control, so that the bolt holes which is already pre-prepared will match with the plate in another one. Extremely difficult, complex. Only by such a very tight regime of geometry control the whole thing could be achieved. But they had finally done it. So this is the kind of things. And then this is the piece are to be put on the top of the pylon, which will take the bearing. It's a base plate for the bearing, which also has been created and brought here and put it on the top of the pier. This is the typical, this is the yard on which the work was going on. You can see the kind of space that is available. This is right on a Yangtze River. Right from there, they got a 4-kilometer long berth, from where they will complete and load it on the ships and send it to every part of the world. So that is the kind of huge facility these people have created for welding. And for each of these plates which come here, we take samples, and these samples were to be taken. And on this, both impact and tensile had to be done. You can see both the things. Pieces are there for tensile testing as well as for impact testing. These pieces are collected from each of these plates, and then they are subject to impact test, the tensile test, as well as the impact test. And this the welding is going on at the same time. Testing is also done by 3 methods up to welding. I mean, up to X-ray test, depending on the importance of the joint. And this is the kind of fabrication facility they have. Most of them are automated, but at the same time, a whole lot of manual intervention is also required. Most of the welding is automated, and it has been done by them very successfully. And the pieces were created and started coming out, checked, and this is one of the legs of the pilot. So facilities like this, they have a lot of welding space. They were practically the entire factory had to be dedicated at one time, so that all these pieces were simultaneously being done. And work that I told you was one of the issue was the two surfaces had to mate together, and the level of accuracy was a millimeter, less than a millimeter for every meter, for a length like 20 meter, 15 meter, 12 meter, like that one, which was the one of the most challenging work, because you do it and the entire surface, this is almost 16 by 12 surface, and that the whole surface has to be brought into that kind of an accuracy, then only it will mate with the other. So several times they had to do this work, such a huge piece. Only after fabrication this planing can be done through a milling machine, and that itself cost a whole lot of them, because on our insistence they had to bring two machines brought from Italy to do this job. And you do the planing, take it out, assemble them, and see there are problems, bring it back, redo the job and take it back. Such a painful, laborious work, but it has been achieved by them due to due diligence from our geometry control and quality assurance people and our supervising people there. So this is the kind of surface they created by planing, the accuracy they got by shear. You can see the size of the surface which had to be mated, and the amount of accuracy it had to be obtained, possible only through machines like this. You can see the one piece is being planed, and the simultaneously this is the machine which is doing this job, doing this job, and see that your accuracy is all monitored in a monitor. You can see the whole operation. You don't have to stand there. You can see from the monitor, sit there and see every millimeter part of it and get the accuracy of the machining done. But at the same time, after doing all those things, when you go out and assemble, which you are going to look at it there were many times errors were there. You had to reassemble, decouple, and bring it back and do the work again. Okay. Then one of the major issue is the trial assembly. All the pieces that has been done had to be assembled once to check the accuracy of the joints, and then only it was allowed to ship. So after fabrication has been done, two more important steps were to be done. One is mock assembly. Piece by piece it will be assembled, checked, and geometry checked that everything is fine. If it is not there, take it back into the workshop, redo the whole thing, bring it back and reassemble and check it. Once only it is passed, you will be allowed to go into the paint shop. So only after the entire whole lot of huge pieces are checked by mock assembly. Very piece by piece it is mock assembled, and once only when it is completely satisfactory to the QA, it will be allowed to go into the paint shop. So this has been done. So this is one of the two iron legs plates are being connected. You can see the huge assembly which has been done here. Mock assembly of various elements. So this is the pylon leg that we've been we have been discussing. Base is getting done, and this is the entire deck is trial assembly has been done, and only after everything is set, you can see the deck here, right, going through the pieces. This is the central, the whole thing had to be completely assembled there, checked each bolt hole, that everything, check bolts have been placed there, you can see, and only when everything fits, everything done, everything corrected, this will be taken into the paint shop, painting itself. And then before that itself, we have do the shear connectors in most of the deck beams. Shear connectors also, it was decided that shear connectors will be done in China itself before bringing it, even though it creates a problem of logistics. It was decided that it will be done here because thousands of shear connectors have to be done. It will be very difficult to do it once it comes to India, because it will spoil the painting also. So it was decided that the shear connectors were also will be done, and then it will be, you can see the mock assembly of a very large portion of the support, pylon support, and both sides have to be assembled and see that it is accurate up to millimeters and before it is taken. This is another shot of the mock assembly. And then once it has been done, this will be taken to the paint shop, which is the completely covered area in which no dust, nothing is allowed, and painting will be done. 4 layers of painting have to be done, and each layer will be washed by the QA people. They will come and test it. Each layer has been done, and each of the 4 layers were given different colors, so that you will know, one look visually itself, you will know whether the painting has been done properly or not. So each of the 4 layers had 4 colors until the final color came. and then the machines are there. The profiles can be checked by the number of tools, equipments. So painting was checked very thoroughly before this one allowed. Otherwise, this is the primer coat, and then the slip. I mean, the bolt also we had to do a testing for slip factor before we take up this one. So this is the paint shop. No air circulation, nothing. It is totally an enclosed area. Painting is to be done with machines. One by one, the layers will be done, tested, and the final coat, paint finished coat comes and it comes outside. And from there, before it is shipped, again an audit is done of the everything. After even after the sandblasting, the profile is checked and then only it is allowed. So painting is done again. This is a small shot about the precasting of the, while fabrication is happening in China, precasting of the deck was happening in our site at Wazirabad, being done one by one. Noted, this precasting is done. You can see the shear connect, the interconnectors here. Sorry, and parallelly the manufacturing of bearings were going on, both the main bearings as well as the pendulum bearings, because only after the bearings are available we will be able to carry out the erection. Next step is transportation. These elements are huge. One of the elements is 450 tons, and other pieces may be small but in size, large sizes. Something like 30 meter and 35 meters, 36 meters, like that one. So logistics was a major problem, but it was decided that these pieces will be shipped from Shanghai to Kandla port, and from there it will be brought to the site by road. This has been decided, and that itself was a huge logistical issue. We have to cover about 1,590 kilometers with a weight of 450 tons along the roads, and most of the bridges and culverts along the road could not take this load. And there, he had to create special facilities, temporary bridges, temporary culverts, to carry this the huge weights of this kind of load. And it took almost 2 months for after extensive route survey and reconnaissance and corrections, the pieces were brought to the site. The methodology, construction methodology, was decided right at the beginning before the design started. On a large scale, it's like this one. You do the foundations first, and on the top of the foundations put the bearing, and the whole of the assembly will be done by a huge crane, using a huge crane of 1250 tons capacity. At that time, such a crane was not available in our country, so this has to be brought from abroad. And the cost of keeping it there itself was a huge thing. Very costly rentals were to be there, and the crane control was being controlled from 2 countries, both from from Asia as well as Europe, and that is the kind of equipment was required to assemble the pieces here. And then after the bearing, you will put the first connectivity, the connectivity under the pylon, and simultaneously the deck will start for the stability to either side. So this has been the plan, and then the deck will be cast so that you get a base here, right base here, and then the next way the temporary supports will be there, and then the next piece will come. They will be connected, temporary connection. These are all enabling structures, and it goes and meets at the junction of the two. At that time, there will be a temporary support for this one. We'll have a look at it, and then the vertical pieces will be done. Then once it reaches there, you start after the first piece, the cabling will start in place. So the second piece, third piece, and like that, the pylon will grow like this one. So this has been and finally the viewing deck. And by the time both the 16 cables in the front and the back stays would be done. So this has been the construction methodology agreed by all the parties, and this has got into the structural design, in detailed engineering, as well as fabrication and erection methodology, everything. So this is the way the construction methodology get into the whole system. It was agreed by everybody, and there is no question of any change later. So this is the way it has been done, and the project is complete. So this is the way the project has been loaded on this carriers, trailers, and then brought over here. These are trailers which has got completely hydraulic equipment, so the load is distributed equally into each of those axles here. Some of them are 16, some of them are 24 axles. The whole weight will be distributed equally using hydraulic jacks, and then brought in here one by one. The sequence has been decided, put on the thing. This is the first piece. which is brought here. This has to be kept in place. The first piece after the bearing, the first piece had to be brought in here, and on the bearing here, this is one of the biggest bearings in the world, 6,500 ton capacity bearing, spherical bearing, which has been placed here. Over that, the first piece of 450 tons has been there. It is an unsymmetrical piece which had to be kept in place through an anchor here. So this is a tie-down arrangement. With that, the whole thing has been placed exactly like this one, and then only you could start the first piece. In the process, the first piece was to be welded. There's no bolting connection allowed. It had to be welded on this one. This itself was a huge job because it had to be done at site. This is the base plate which has been done, been concreted, and then the first element of the piece has to be done. This has to be welded in place. Huge piece, welding through the day, through the night, and the for which you had to do the completely, the area has to be covered, and underneath the preheating is to be done, because that's very important that the temperature is controlled, and then a sequence of welding is created, a proper procedure is there, and then very highly qualified experts were there. In fact, we got one gentleman from Germany who has overseen this complete welding. We had difficulties once or twice, the rework had to be done, but at the end of the day, successfully the whole thing was welded and we came out successfully. And this is the pendulum bearing being erected in place. It has come from Germany and it has been put, it's trying to put it there. You can see the pendulum down and finally assembled there. And this is the way a turntable has been created so that the segmental erection could be done. And you can also see the painting that has been done here, because there's a decorative painting had to be done. This is already done in pieces before erection. This has been done at site by an artist, specially commissioned. The artist will tell his name. And one by one, the legs are coming up, and you can see the growth just as planned in the construction methodology. One by one, the pieces are in place, and you can also see the working platform, these temporary structures that you see there with the railing, so that people can stand there and do the connection, do the bolting, and check the assembly. And one by one, all these structures, pieces come, get assembled and goes forward, reach the kink, whatever we call it, because the two legs join there, and the vertical part of the pylon rises there onto which all the cables are connected. You can see the big, huge crane standing there, and the river is slightly in spate at that time. The construction reached that kink level. From there, the first vertical piece has come onto the top of the kink at the incline level. This has been the most difficult thing, because the complete mating is to be done for a length of almost 20 plus meters, and it had to join there. Once it is closed and put there, every one of those bolts had to match. There is no way, not even a single bolt. But fortunately, and they must congratulate all the people who have worked in this one, that there was no such problem of a mismatch. That is because of the tight geometry control, tight quality assurance, and tight work during the assembly, mock assembly, which has been done in before shipping here. Hats off to them. And then one by one, the pieces are in place, coming above, and we reach almost the top level. And by the time the cabling is also being done, I'm not going deep into cable because that itself is a subject. And by that time, what we do is, for each one, we have to do a stage by stage construction analysis. Every time a piece is placed there, it affects the geometry of the structure, because a load is coming onto that one. There will be settlements, there will be deflections, and everything will be there, and that has to be taken into account, checked with the design, final alignment, because after all those things, when it is completely put it, you have to get the alignment back. So a stage by stage construction analysis is required before you put the piece. Then analysis is done, and then after it is put there and it's verified, and then only the next piece is put. So this is a parallel analysis which is going on. And similarly, using a Goliath gantry, the deck has also been created to both the places. And fortunately, without much ado, the project is getting completed slowly. You can see near completion stage there. You can see most of the deck is also getting completed. The cables have been completed, of course. The various works are still going on. The top piece is still not there, and the road is almost ready. Even though the top viewing gallery is not ready, the road is almost ready to be opened, nearing completion. And this is the way it looked at that time. You can see the western approach clearly on the left hand side. The complete western side is there, and on the right side the embankment starts almost completely done on that side also up to Kajuri Khas. You can see the Wazirabad barrage on the right and the bridge standing up. And this is the way it will look. It was look at that time, and the graphics which has been done. It is a very sophisticated way it has been done. We tried to create the Yamuna's background, the cultural background of peacock feather on this one. So by very ingenious methods, the painting has been completed of peacock feathers, and it is clearly visible there. And it was done before assembly, so you can see them later as it stands today. So this is, you can see both sides of the bridge. When it is completed, an aerial view, you can see them. And this is now the bridge stands in all its glory, and you can see while going through what feeling you have. Now you can see there are only two sets of cables. If there were two decks, this would have been a complex thing, because you will see a whole lot of complex cables coming helter skelter. So this made it very beautiful, because once you go through, the cables fly past you without any bothering the eyesight. So this was the idea, and this is the advantage of two plane cables. And you are almost getting the Namaste through. And the bridge was inaugurated on 4th of November 2018 under a lot of fanfare and a lot of problems also. The project was inaugurated by the Chief Minister of Delhi on the 4th of November. And the bridge looks like this when lighted. And these are various views of the bridge after lighting. This is you're getting Namaste through. Again, this is the way it looks now. Completed, all the enabling works removed, and the viewing gallery on the top is also done in glass. And this is the way it looks now. And another view of the bridge. You can see the peacock feather painting on the structure. Looks very beautiful. This is another aerial shot with all the other elements in place and the river, and one closer shot of the feather painting on the structure. And if you look at it, the cost part of it, I will not go into the actual cost. The foundation and substructure was about 10%, and the reinforcement, the superstructure cost us about 30%, reinforcement about 7%, steel pylon 34%, stay cable 9%, bituminous work 3%, expansion joint and bearing 5%, and glass facade about less than 1%, and other miscellaneous work about 1.27%. That makes the project complete. So this is the way the project was quantified, and this one. And hats off to these people. Whole lot of people worked on this one. The basic design was done by Schleich Bergerman and partner. I must give my tribute to the York Schleich, who came first here. I told you the story later. He's quite senior even at that time, but a very passionate man who spent an enormous amount of time in Delhi and Germany to create this concept. I give all my tribute to him. Tremendous amount of effort, tremendous energy, sincerity. He has created this one. Then the Construma Consultancy Private Limited with Subbarao, Dr. Subbarao, who has created the entire foundation design from India, Bombay. And our friend Ratan Batley Boy Associates, a wonderful urban architect who has spent enormous amount of time during the evolution of the design. And his contribution cannot be forgotten. A lot of work has been done by him to get an acceptable design. And the proof consultant was, we are fortunate to get the joint venture among Sistra Consultant, but we could rope in Michel Verloju, one of the tallest bridge engineer in the world, who has created the Miao Viaduct in France. And he has been kind enough to work with us for proof checking the design, and assist them from the Indian side was the Tandon Consultants Private Limited with Mahesh on the lead. And detailed engineering, we are very lucky to get the Studio di Miranda under Professor Miranda. Fabulous man, spend any amount of time and any amount of discussions unruffled with all the details he has to done. Tremendous work has been, contribution has been done for both the detailed engineering and the complete enabling work design was done by Professor Miranda and his team there. The other consultants was the entire geometric investigation was done by Stoop Consultants. The geometric design was done by Eller Kadiali. Unfortunately, he is no more. A wonderful person. He has spent his time with us a long time, which could create this. All those bottlenecks was created. I mean, cleared to get a beautiful signal-free project. Seismic study was done by an Indian IIT Roorkee, and they have done a complete site study, site investigation, and they create a site-specific spectrum was created, and complete report on the seismic study was done by IIT Roorkee. The wind tunnel study was enormous work done by Rakers Engineering, Germany, in their wind tunnel. Hydraulic model studies were by CWPRS in Pune. About 3 or 4 times we had to sit with them and create models and test them. The third-party quality assurance is done by Lloyd Register Asia. Wonderful work done by both in India as well as in China. Important work. The other vendors, the fabrication and pylon and deck was done by ZTSS China. The cranes came from Zeren's heavy lifts. The bridge bearings were from Morer Jone, Germany. Expansion joints from Mageba, Switzerland. Stay cables came from Tisca, Spain, after a lot of difficulties. Initially, we had to source from somewhere, but the testing it failed. So we had to go to Tisca to get this one. The high HSFG bolts were supplied by TVS fasteners. We have a lot of discussions with them. They were evolving. Finally, they have supplied all the bolts from Chennai. Railing and steel fabrication by Rajhans from UP, and structural steel, other enabling structures were done by, again, Saifi Steel, UP. Specialized agencies were Radielli, Italy, for railing around the pylon, Grapiel platform flooring pylon, Calzip were for the pylon roofing, advanced bolting solutions for tightening the bolt is a very, very involved and very accurate work be done by a team. SRA infrastructure for the glass facade, Buma Korea for rigs for drilling into the rock for our famous P23, Fortain France for tower crane, and Dr. Deb Bilal Gupta, who has done the wonderful graphics on the pylon surface, a very, very sensitive artist. And the construction agencies were, a main bridge was a JV among Gammon from India, the oldest construction company in India. Construtora Cidade from Brazil and Pensechai from Italy. And the approaches were done by, again, Gammon engineers and contractors private limited. Lifts were done by Maspero, Italy. Pylon access system by Oriental Engineering Works, and the bridge health monitoring by Mageba again. So that's the thing. So it was a huge participation, global participation promoted in 14 countries, coordinating all by a construction management team. This was the core team. You can see the proud Gammon Hede and our project manager at that time, Mr. Bansal, and Mike Fleisch, who is the son, and the main work has been done by him from Germany and for the Schleich. And Subrao is not there. His son is with us. Harsha, always several discussions we had. Some of the toughest problems were solved by his office, like P23 and our MD at that time and myself, and our architect Ratan Bartley Boy and Professor Miranda. A proud moment for all of us. And the whole of the construction management with all these complexities were done by the engineering wing of the Delhi Tourism and Transportation Corporation. And then the entire, I'm proud to say that all the engineers of DTDC were on deputation from the Central Public Works Department. So with that, I conclude, and I thank you very much for patient listening. I'm very sure you will not be satisfied because each of these elements require elaboration, and I had to rush through because of the time limitation. Maybe some other time, if it is possible, we can meet again and discuss each of the elements, because each one of them teaches us a lesson, and each one of them was the hard-earned solution to tough problems. So thank you once again for all the attention. I thank QCrete and Shelly Fernandez for the opportunity given to me again. Thank you. Sir, I leave it to you now.
Good evening. Hello.
Yes.
Yeah. Good evening. Wonderful lectures, sir. Thanks a lot for being with us today. And I hope the civil engineering community will appreciate this wonderful presentation that we had for last 1.5 hours. And appreciate the audience and all the civil engineering community for having come and attended this beautiful lecture by Jose Korean sir. So, any questions forward to us? We will from our Jose Korean sir. Get back to, for coming on this weekend and attending this wonderful lecture. Thank you, Jose Korean sir, once again. Thank you.
Thank you very much. Thank you very much. Are we closing or are there any questions? Hello.
Yeah, questions we'll send it to you.
Hello, I think you can. Yeah. We'll send you the question, sir. Yes.
Yep.
Yes, sir. Korean sir, we'll send you the questions once it is through. We'll send it to you.
Fine.
Okay.
Fine. We'll answer.
Thank you.
We'll answer.
Thank you, sir. Thank you very much. Thank you very much for the session.
Are we closing? Are we closing?
Yes, sir, we close it. We close the session.